Hi, welcome to a lecture on section 2.5 on non-homogeneous equations and undetermined coefficients. So we've looked previously in section 2.3 on how to solve equations like this that are homogeneous. So they're linear equations with constant coefficients, but the right-hand side is 0. And that's called a homogeneous equation. And we're now want to learn how to find a solution for an equation that's not homogeneous. So an equation where there's some function of x on the right-hand side here, or just something that's not 0. So recall how we solve these types of equations. So I think we learned, it was section 2.1 or 2.2, I think, where we learned about how our approach to solving equations like this is going to be the following. We're first going to get a general solution for this homogeneous equation, and that's called the complementary solution. So the complementary solution, and we represent that with y sub c. So that's the complementary solution. So we completely solve this equation first, get a general solution for it, which involves getting n linearly independent functions that satisfy this equation. And that means we'll have n unknown coefficients, c1 up to cn. And those are going to be determined by the initial conditions. Then the next thing we need to do is we don't need to find, we just need to find one solution to this. And it doesn't need to satisfy the initial conditions. So the initial conditions are going to be taken care of by this complementary solution and those coefficients that we need to determine. So any particular solution of this equation is going to do just fine. So that's all we need, is just a single particular solution of this non-homogeneous equation, and we refer to that as yp. So these are the two pieces that we need in order to solve this differential equation up here. We need this complementary solution of the homogeneous equation, and then we need this particular solution of the non-homogeneous equation, and that gives us a complete solution to this non-homogeneous equation. It is precisely the complementary solution plus the particular solution, and that gives us a general solution for this non-homogeneous equation. So that's just a review of the strategy that we use to solve these types of equations. So in section 2.3, we talked about this. So we know how to do this from section 2.3. So recall what we do is we write down the characteristic equation, we find the roots of that polynomial, and then those roots tell us precisely what this characteristic equation is. It's very straightforward. So now the last piece is how to find this particular solution. So how do we do this? There's a couple of different methods. So let's start out with the first method, called the method of undetermined coefficients. Now, in this method, there are some restrictions on what the f of x could be that's on the right-hand side of the non-homogeneous equation. So that f of x needs to be products of a polynomial, an exponential, and a cosine or a sine function, and then we can add up a bunch of those types of terms. So it's a sum of products of a polynomial, an exponential, and a cosine or sine function. And if f of x is of this form, then this method of undetermined coefficients is guaranteed to do the trick, and we'll be able to find a particular solution. Okay, so what is this method? So it's very straightforward. What we do is we take this function f, maybe I should highlight this because this is kind of an important thing to focus on. So we're focused on this f of x. So what do we do with this f of x? Well, we consider all the terms that appear in f of x and in the derivatives of f of x. Okay, and we just write them out. So I'll do some examples of this, but for now, I'm just imagining that we have a complete list of all the terms that appear in f of x and in the derivatives of f of x. And in particular, what we're looking for is a set of linearly independent functions here. So we'll see in the example. We'll do a lot of examples of this, so you'll see. Now, there's one thing that we have to be aware of, that if one of these functions that we have in this list is actually a solution of the homogeneous equation, that's a problem. It will end up disappearing when we substitute it into the differential equation. So it doesn't actually contribute anything. It's kind of like a redundant solution. So what we do is we do the trick that we saw from before, where when we had double roots, we replace this function with x times that function. And that's it. That's basically it. So once we have our list of functions, where after we've done this replacement piece here, then we form this linear combination of those functions that we got from this list. And we simply substitute this linear combination here into the differential equation. And in doing that, we'll determine these coefficients, a1 up to am. Okay, so that's kind of the general idea. So let's look at an example of how this is done in practice. So I'll do a few examples where we'll find a particular solution of this differential equation. Now, the first thing you have to be aware of is, because of that caveat that we need to find functions that are not solutions of the homogeneous equation, the first step is going to be to determine all the solutions of the homogeneous equation. So then we can be able to refer to that and decide if something satisfies the homogeneous equation or not. So how do we do this? So we know we just write down the characteristic equation. We find the roots of that equation. So we have plus or minus I4 or 4i, however you wish. And so then this tells us that our general solution of this homogeneous equation is going to be yc equals c1 cosine 4x plus c2 times sine 4x. So there's our general solution. So if we have if we end up having something that looks like cosine 4x or sine 4x, then we know that that's going to satisfy this homogeneous equation. Okay, so now what is our f of x? So here the f of x is equal to this right-hand side, e to the 3x. So let's look at f and all of its derivatives. So let's maybe write like a, let's see. So we'll start with f of x equals e to the 3x. And then we'll take the derivative of this, and we'll get 3e to the 3x. Now, with these coefficients, I'm not going to pay attention to those, because when we end up forming this linear combination up here, we're going to add like arbitrary coefficients in. So any sort of coefficient that appears in front of a term like this, I'm just going to ignore that. So when I look at the derivative here, I'm just going to, so first of all, I'm going to take this term here. So that'll be my phi 1 of x is going to be e to the 3x. And then when I look at this term, I just get another e to the 3x as a term, but I already have that one. So, and you can see that if I keep going with taking derivatives, all I'm going to get are just, well, the next one will be like 9e to the 3x and so on. So it's all going to be just some constant multiple times e to the 3x. And so this is the only function that we need to consider to find our particular solution. Okay, so therefore, that's our list of functions. Maybe I'll put like a box around it to make it clear. That's our complete list of functions. So therefore, y sub p is a1 times this phi 1 of x. So it's just e to the 3x. Okay. And I was just checking on my dog. And now we'll substitute this into the equation. So let me just put a box around this. So there's our y sub p, and we just need to determine this coefficient a sub 1. So let's substitute this in. So first of all, y p prime is equal to 3a1 e to the 3x, and y p double prime is 9a1 e to the 3x. Okay, so let's substitute that in. So our differential equation is this one. So let me just grab that, bring it down here. Let's see, just make that blue. How are you doing, dog? Okay. All right, so let's substitute this in. So we'll have the y double prime. So maybe I'll put the p here because that's what we're substituting in. So y double prime p is equal to 9a1 e to the 3x plus 16 times a1 e to the 3x, and that's equal to e to the 3x. So in total on the left-hand side, we're getting, let's see, 9 plus 16 is 25. So we'll have 25 a1 e to the 3x is equal to e to the 3x. And in order for these two terms to be equal to each other for all x, we need the coefficient of this term, which is this 25a1, should be equal to the coefficient of this term here, which is 1. So I could write that in, just put a 1 there, 1 times that. So therefore, we get that 25a1 is equal to 1, and that implies that a1 is equal to 1 over 25. So there's our coefficient that we need. And so therefore, our function y sub p is equal to 1 over 25 e to the 3x. And there's our particular solution. And in fact, at this point, we might as well just state what the general solution of the differential equation is. So I'll just continue. The question didn't ask for this, but I think it's interesting to write it down. So to get the general solution, we just add the complementary and the particular solutions together. And that is going to be equal to, well, let me just write it this way. So it's not really therefore, but let's just continue. So this, maybe this, trying to decide how to write this. So then this implies that y is equal to c1 cosine 4x plus c2 sine 4x plus 1 over 25 e to the 3x. And there it is. So that's the general solution of this differential equation. Oops, that's not what I wanted to do. There it is again. Just wanted to move this over a little bit. So there's our general solution to the differential equation. If we had some initial conditions, we would use those initial conditions to determine these coefficients C1 and C2. And that's the purpose of this term here, really. It's because we want to find, we could get any kind of initial conditions, we want to find a function, a general form of the function which can satisfy any possible initial conditions that we are given. So this is the general form. This is a particular solution. It has some initial conditions which may not be the ones that we want, and so therefore we have to have this complementary solution there, and that does the trick. So there's our general solution. Every solution of the differential equation is of this form. Okay, so that's one. Now let's do another one. So again, we start by writing down the homogeneous equation and then writing down the characteristic equation and finding the roots. Is this easy to factor? Maybe like this, I think. Yeah. Okay, yeah, I think that's it. So then the roots are going to be, I'll just put them in order, -1 and 2. And so therefore, the general solution of the homogeneous equation is going to be C1 e to the negative x plus C2 e to the 2x. And that's our general solution. Maybe I almost want to like highlight this. So I forget what color I was using. Anyway, maybe I'll just leave it like this. So there's our general solution of the homogeneous equation. Okay. So remember, if we have any possible term that we're going to use in our particular solution, if it matches like this or this, then we're going to reject it and replace it with something else. So we've got this, and now we can go ahead and write down our function. Let me just box this off. So recall that our function is f of x is equal to 3x plus 4. Okay, so maybe we could write kind of like a table. We have like a kind of like a table where we sort of have like, derivatives of f of x here. Yeah, why not? And then over here, we could have like the term phi that we're getting. Might be a good idea. I don't know. Maybe that's kind of confusing. I'm never really sure how to organize this stuff. So let's just start taking derivatives and see where that takes us. So first of all, from this function, I see that there's two terms that are in this function that we want to pull out. So there's a 3x term, and we're going to ignore the 3 because, as I mentioned, we don't care what the coefficient is of these terms. We just want the term itself. So there's one term there. It's going to be x. So that's one term. And then there's another term. There's a 4, and that 4 is actually like 4 times 1. And so that'll be our second function that we are going to, a second term that is appearing. So here are the two terms. So we have the x and the 1, and that gives us our two terms here. And then we need to also look at the derivatives of f. So we have to go through and look at all possible terms that appear in derivatives of f. So we'll end up getting 3, and that's just times 1, so we already have that. So we don't need to do any more there. And then I can take one more derivative and I get 0. So again, there's no terms there that we need to add in. So these are the only two terms, x and 1. And so therefore, our particular solution is going to be a1 times x plus a2 times 1. So there's our particular, the form of our particular solution. And then we just need to determine these coefficients. Okay, so let's substitute this in. So first we need to take some derivatives. So y prime, yp prime and yp double prime is 0. Okay, and now we want to substitute it into this differential equation here. So I'll copy this and I will put this, I don't know, let's see, maybe I've got as much room as I need really. So why don't I put it here? If I need more space, I can just add another page. So this, there we go. And yeah, I do need to add a page here. So let me just squeeze it in another page right here. And then there's always this bug in this program. If I, oh, maybe they fixed it. Yeah, let's just see if, let's see if there's a, I don't see it in screen capture either. So it's probably okay. All right. So, so now let's substitute everything in. So remember, this is, we're substituting in this particular solution into this differential equation. So y double prime is 0, y prime is a1, and this will be 2 times a1 x plus a2, and that is equal to 3x plus 4. Okay. Now, let's see. So let's simplify this. I guess I want to put all the x terms together. So I get minus 2a1 x. Let me just put this on the second page here. And then the other terms, I have plus, oh no, it's not really a plus. Well, I should probably put it as a plus. So it's going to be plus minus a1 minus 2a2. And then that's equal to 3x plus 4. Okay, so now we just match up the coefficients. So you're probably familiar to doing this kind of thing. Let's see. Let's match these up. So this coefficient here, that's going to match up with this one. So minus 2a1 has to be equal to 3. And then the other one, which I will do in, I better not do blue. Let me go back to orange again. And this term here is going to be equal to this one. So let's just write those down. So in order for this to be equal for all x, we need these conditions to hold. So therefore we have negative 2a1 is equal to 3. Why don't we just solve that right now? So that's a1 is equal to negative 3 over 2. And let's see, then we have negative a1 minus 2a2 is equal to 4. But we know that a1 is already negative 3 over 2. So we get negative 3 over 2 minus 2a2, let's see, equal 4. And what does that give us? So that'll be 3 over 2. And then I guess I could divide both sides by 2. So I'll get 3 over 4 minus a2 is equal to 2. And what's next? I guess move a2 over to one side and bring the 2 to the other side. So that'll give me a2 is equal to 3 over 4 minus 2. So it's 3 over 4 minus 8 over 4. So it'll be negative 5 over 4. So a2 is equal to negative 5 over 4. So there's our a1 right there. And this is a2 right there. And so therefore, our particular solution is going to be a1, negative 3 over 2, x, and then plus a2, which is negative 5 over 4. And there's our particular solution. Yeah. And I keep skipping this, by the way. So in the last one, I did it as well, because when I got these terms, I didn't actually, mentally check. But I mean, these terms here, x and 1, they're not equal to x to the negative 2, e to the negative x, and they're not equal to e to the 2x. So that's why these were both acceptable. So but yeah, so I just remember that, because I'm going to now, let's take this complementary solution and write the full solution here. So then y is equal to yc plus yp. And so that implies that y is equal to c1 e to the negative x plus c2 e to the 2x minus 3 over 2x minus 5 over 4. And that's it. There we go. So that is our general solution to the differential equation. So there's our general solution right there. Okay, so the question is just asking us for this particular solution, but why not, right? Why not write down the complete solution right there, since we already have the complementary solution? Okay, so there's another one down. So now let's look at this one, and this one is going to bring in that concern that we have when we end up with a function which is a solution of the homogeneous equation, and then we have to do something. So let's see. So let's start by looking at the homogeneous equation. Write down the complementary solution. And then we get r is equal to plus or minus I3. And so therefore, the complementary solution is going to be C1 cosine 3x plus C2 sine 3x. So there's our complementary solution. And now f of x is equal to 2 cosine 3x plus 3 sine 3x. Okay, and I'll just start by taking derivatives until I'm sure that I've got all the terms that I'm looking for. So if I take the derivative of this, I'm just going to get, let's see, negative 6 sine 3x plus 9 cosine 3x. Okay, and so I ended up getting the same two terms again. And I know if I keep taking derivatives, I'm just going to keep getting terms that are like cosine 3x, sine 3x. So when I take the derivative, I get sine 3x, I already had that, and cosine 3x. And if I keep taking derivatives, I'm not going to get anything different than those two functions. So those are my candidates for phi 1 and phi 2. So I'll have cosine 3x, and we have sine 3x. But now, if we look back up here, we see that both of those are actually solutions of the homogeneous equation. And I mean, I could go through the process of like writing down the particular solution of this, a1 cosine 3x plus a2 sine 3x. If I write that down and substitute it into the differential equation, I'm going to get 0 on the left-hand side. So all of my a1 and a2 are just going to disappear. I won't be able to solve for them. So how do we deal with this? And there are reasons why this is reasonable. We're not going to go into that so much. It's very similar to that trick that we saw with repeated roots. So I'm going to ask you to trust me on this, but both of these functions need to be rejected. So I'm going to reject this, and I'm going to reject this because they are both solutions of the homogeneous equation. So maybe I'll make a note of that. So reject since both are solutions of the homogeneous equation. Okay. So what's the answer then when we have to reject them? So then we just multiply by x. So we're going to take, instead of cosine 3x, we're going to use x cosine 3x. And instead of sine 3x, we're going to use x sine 3x. Okay, so where is this coming from again? So let me just go back here and just make this connection. So this is from this requirement right here. So this requirement, this is what I'm referring to. If some function is a solution of the homogeneous equation, replace it with x times that function. So that's what we're doing. Okay, so let's move back to where we were. A little too far. So there's our two candidate functions, and now both of these are fine. Sometimes when you multiply by x, you'll get another function that's a solution of the homogeneous equation, but in this case, these are both fine. Maybe I'll go back up here and I'll just indicate that when we had these functions here that we were satisfied with them because they didn't satisfy the homogeneous equation. So let me put check marks. There's just one function here, so let's put a check mark there. So that's to indicate, let's make sure they're not solutions of the homogeneous equation. If you ended up proceeding with things that were solutions of the homogeneous equation, you may be in a situation where you're not able to satisfy the differential equation. And then that'll tell you that you've maybe forgot about this step. Okay, so there we have it. Did I put a box around those other ones too? Just trying to be as consistent. Yeah, I did. I put a box. I like putting boxes around things. Okay, so there we have it. We have our two functions that we need. And so therefore, y sub p is going to be a1 times x cosine 3x plus a2 x sine 3x. Okay, so that's going to be the form of our particular solution. Okay. Oh, see, yeah, I'm getting that. What's really funny is that this stuff here, it's appearing on the screen capture, but it's not. If I show you my my iPad, you see that it's not there, right? So you see I'm drawing here. There's nothing on my screen, but it appears on the screen capture. So it seems to be some kind of a bug. So what I do to fix it is I just hop out and then I just hop back in again, and it seems to fix it. So that's the trick. Sometimes we just got to live with these bugs. Maybe it's not a bug, it's a feature. It could be that. How you doing, Jana? All right. Let's see. Okay, right. So what are we doing? we are now plugging that into this equation here. So copy that and I'll bring it down. Oh, I guess before we do that, we're going to need some derivatives. So we will just put that here for now. Let's compute a couple derivatives. So we need y prime. We don't actually need y prime, but we'll need it in order to get y double prime. So let's compute y prime. Let's see. I'm just trying to think, instead of doing like two product rules, I feel like it would almost be better to factor an x out and then just have to deal with a single product rule, because who likes product rules? Nobody. X times a1 cosine 3x plus a2 sine 3x. Okay, my dog, 1 second. Well, maybe I'll let it keep recording. She's appearing on camera. What's up? There's nobody out there. It's dark. I'll leave the door open slightly in case she wants to come back. All right. Okay, so let's do this. So now we have just one product rule, much better. So normally, like I like taking the derivative of the first thing first, but it seems like most people like doing it the other way. So I'll just write x times the derivative of what's in the parentheses. So that'll be negative 3a1 sine 3x plus 3a2 cosine 3x. Oh, now I'm doing product rule. Almost forgot. And then derivative of x, which is 1, times a1 cosine 3x plus a2 sine 3x. All right. Just move that up a little bit. Can I like rewrite that in a nice way? Because I have to take the derivative of that again. I don't know. Oh no, my Apple Pencil battery is low. Hopefully it doesn't die before I finish. Let's see. I don't know. I guess we could. Well, if it's just a matter of like product rule that I care about, then I suppose I could just leave it the way it is. Yeah. Yeah, okay, let's just take the derivative of that the way it is. I'm always kind of looking for shortcuts, whatever is easiest here. Let's see. So again, the first times the derivative of the second, which is minus 9a1 cosine 3x minus 9a2 sine 3x plus 1 times minus 3a1 sine 3x plus 3a2 cosine 3x. And then I need to take the derivative of this last term. That'll give me a negative 3a1 sine 3x and a 3a2 cosine 3x. Did I do that right? I think so. I think that's okay. But this thing we should definitely simplify before we substitute it in. Oops. Y prime, y double prime. Let's grab all the cosine terms first. So what are all the cosine terms? Let me highlight them. So there's a cosine here, cosine here, cosine here. Okay, let's bring all those together. So what are the coefficients? I get negative 9a1x plus 3a2 plus another 3a2, which is 6a2. So that's just 6a2. So that's the coefficient of cosine 3x. And then what is the coefficient of sine 3x? Sine 3x, there, and there. Coefficient is going to be negative 9a2x minus 6a1 times sine 3x. Okay, that's good. All right, let's use that. All right, now we're going to substitute it into this equation here. So there's our differential equation, and let's substitute these things in. So just going to be lazy. I'm going to copy this and then paste it right here. And I also need plus 9 times yp. And again, I'll just copy that, bring it down here, and paste. And that is equal to 2 cosine 3x plus 3 sine 3x. All right, what did I highlight? So sine I highlighted in green. So let me highlight that. So there's a sine 3x there, sine 3x there, sine 3x there. So what does that tell us? And then let me do the other highlighting as well. So the cosine. Cosine 3x is right there, and right there. Okay, so let me simplify that left-hand side. So this is going to be minus 9a1x plus 6a2, and then plus 9a1x. Oh, that's gonna cancel that. And then the sine 3x is minus 9a2x minus 6a1. And then plus 9a2x. Yeah, don't forget that x. There's an x there. You know, it's almost hiding. I almost missed it both times. And then that's sine 3x. And then on the left-hand side, it doesn't change. It's just 2 cosine 3x plus 3 sine 3x. All right. So there's the cosine terms. And here are the sine terms. Okay, great. Now notice what's happening here. These terms actually cancel. So that cancels that all cancels. So what are we getting? We're needing to add a page. Okay. So what do we get? I think maybe there might be room to fit this in here. So on the left-hand side, I get 6a2 cosine 3x minus 6a1 sine 3x. And on the left, I get 2 cosine 3x plus 3 sine 3x. Okay, let's highlight, I don't know, in red, I guess. So this coefficient of cosine, that has to be equal to 2. And in orange, no, I already did orange. Sort of running out of colors here. Guess I don't want to do blue again. Maybe I'll just do dark green. So there, this coefficient is equal to this one. Okay, so what is our conclusion? So therefore, 6a2 has to be equal to 2, and negative 6a2, a1 is equal to 3. So we get a2 is equal to 1/3, and a1 is equal to negative 1/2. Okay, great. So there's our coefficients, and so therefore the particular solution is going to be 1/3 x cosine 3x. Oh, I did the wrong thing. a1 is negative 1/2. And then plus a2 x sine 3x. There is our particular solution. All right. And so then, y is equal to yc plus yp, which implies that y is equal to c1 cosine 3x plus c2 sine 3x, and then plus p, yp, the particular solution. And that's it. There's our general solution for the differential equation right there. Perfect. Okay, so that's how these things come together. You get a complementary solution for the homogeneous equation. We know how to do that from previous section. And now we use this method of undetermined coefficients in order to determine a form of the particular solution, and then determine the coefficients. In this case, they were negative 1/2 and 1/3. All right, great. Let's do another one. Let's see, I'm just trying to think if I want to start on a new page. Yeah, why not? Okay, so here's another interesting one. This is just to sort of show you all the different things that could possibly happen. So again, we start out the same way. We write down the homogeneous equation. There it is. We write out the, we write out the characteristic equation. And there's no y term, so we're done there. And then we solve it by factoring. Factor out an r. And then we get, let's see, -4 plus 3. Okay, so therefore the roots are going to be in order. I guess it's going to be -3 and then 0 and then 4. So those are the 3 roots. Okay, so then we can write down our complementary solution. Maybe I'll just write it here instead of trying to squish it in. So therefore yc is equal to c1 e to the negative 3x plus c2 times e to the 0x, which is just 1. So c2 times 1. And then plus c3 e to the 4x. So there's our complementary solution. Okay. Let's see. All right, so now we need our particular solution. Okay, so let me grab this function. I almost surely will not remember this. So this is our function. Okay, So we're trying to figure out the form of the particular solution. So we need to look at for all possible terms of this function and its derivatives. So already I see, phi 1 is equal to x. So there's an x term right there. And then there's another term here, x e to the negative 3x. So I'll just write these down for now. I think they're going to have to change. Yeah, I mean this one's okay, but yeah, this one's okay. All right, so maybe these are okay for now. So but we need to get all the terms that appear in f and its derivatives. So let's start taking derivatives. So we have 1 minus, and then we have to do a product rule. Let's see, minus 2x times negative 3e to the negative 3x. And then derivative of the first times the second. I'm going to move these. Oops, that's not what I wanted. I'm going to move these. I want to put this over here. Okay. Yeah, let me just make some more room here until I'm sure that I've determined all possible terms. I think I need to simplify this, do I? Yeah, let's simplify this. So f prime of x is equal to, let's see, 1 plus 6x e to the negative 3x minus 2 e to the negative 3x. Okay, so let me start highlighting some terms that I'm noticing here. So first of all, we have x, and then we have x e to the 3x. So those are two terms that are appearing. This is a new term, 1. We haven't seen that yet, so we need to add that in. So why don't I write that in here? 1. And let's see, what else do we have? So we also have, so we have an x e to the 3x, which we've already seen this one. That's up here, so we don't need that again. But this is a new term, I think. Yeah, we don't have this one yet. So this is a new term. So we need that one. So let's write that in our list. E to the negative 3x. Okay. I think so. If I take more derivatives, if I take derivatives of this, I'm just going to get e to the negative 3x again and again. If I take derivatives of this, well, we've already seen what happens because we did it up here. So if I take a derivative of this, then I'm just going to get stuff that looks like this. In other words, I'm going to get terms like this, and I'm going to get terms like this. And if I take the derivative of this, I'll just get 0. So I think that's basically it. It's just these four terms are the 4 terms that I need. Now let's go through our process of checking to see if any of them are solutions of the homogeneous equation. So let's go up here and check. So what have we got? We've got e to the 3x. Okay, that's a problem. E to the 4x, I think we're okay there. And there's a 1 here, right? This is 1. So we have to reject those. So which ones are we rejecting here? We're rejecting this one, and we're rejecting this one here. Okay, so let's replace them. So phi 3 is going to be x times that, but then that just gives me x times 1, and we already have it up here. So that means that we're going to need to replace that one again. And I think the same thing happens here as well. So if I multiply this by x, I'm going to get x e to the negative 3x, and that already appears right here. So these ones have to be rejected again because we need 4 different functions. These are kind of like redundant functions that we don't want. So we'll need to reject these ones again, and we will again multiply by x. Oops, I don't want red. X squared. And phi 4 of x equals x squared e to the negative 3x. Now, both of these are not solutions of the homogeneous equation, so we don't have anything like x squared or x squared negative 3x or e to the negative 3x. So these ones are okay. So let's go ahead and put our check marks in. So this one is fine, not a solution of the homogeneous equation. That one's fine too. And these ones are also fine as well. So we've got 4 linearly independent terms that are terms that we want to include in our particular solution. So therefore, the particular solution is a1 x plus a2 x e to the negative 3x plus a3 x squared plus a4 x squared e to the negative 3x. Okay, what did the question ask? Determine the form of yp. Okay, so actually we're done at this point because it just wants us to determine the form of yp. And so there is the form of yp that we're after. Now, if we wanted to actually determine these 4 coefficients, we could, but it would be a lot of work. And I think we've got other things to do, but the process is essentially take the derivative of this, how many times? 3 times. We have to take the derivative 3 times, and then we would substitute that into here, 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 and then we would equate everything, and we would solve for a1, a2, a3, a4. Okay, that would be a lot of work. So we're going to stop there. Okay. All right. So now in this one, we're gonna do the full thing. We're gonna solve the initial value problem. So we have a differential equation and we have some initial conditions. So we're going to determine the full general solution of this differential equation, and then we're going to figure out what are the coefficients C1 and C2 that satisfy these initial conditions. Okay, so let's do the full process now. So first of all, again, we always start by solving the homogeneous equation. Let's see, so r squared plus 4 equals 0. So r is equal to plus or minus I times 2. And so therefore the complementary solution is going to be C1 cosine 2x plus C2 sine 2x. Okay, great. And now we will look at the function 2x. So this gives us some candidates already. We have our first candidate is x, so there's a term there. And then if we take the derivative of it, then we get 2, and that's 2 times 1. So we have 1 as well. So phi 2 will be equal to 1. So there's our terms, and we check, are they solutions of the homogeneous equation? No, they're fine. So those are both fine. All right. Okay, yeah, so good. All right, so therefore, the particular solution is a1 x plus a2 times 1. So there's our particular solution. We need to substitute that into this differential equation here. So we'll take the derivative. And we'll take the second derivative. Okay. And then we'll take our differential equation, put it right here, change the color. Okay. So we're going to substitute our particular solution into this differential equation. So y p double prime is 0, and yp is a1 x plus a2, and that is equal to 2x. And so we end up getting 4a1 x plus 4a2 equals 2x. And that's actually 2x plus 0. So when we match things up, we have 4a matches with this 2, and then this 4a2 matches with the 0. So therefore we get 4a1 equals 2, and that implies a1 is equal to 1/2. And we have 4a2 is equal to 0, and so a2 is equal to 0. Okay, great. Add another page. Deal with this bug. There we go. Okay, so now let's see. Okay, so that tells us what our particular solution is. So yp is 1/2 times x plus 0. So this is it. And so therefore, y, which is yc plus yp, I don't know why I don't like that. Let me say then, this implies that yc was c1 cosine 2x plus c2 sine 2x, I believe. I believe that's what it was. Yeah. And then plus 1/2 x. Okay. There's our general solution. And now we can determine the values of C1 and C2 that satisfy our initial conditions. So to do the initial conditions, we will need the derivative of this. So let's go ahead and do that. Okay, there's the derivative. And let's go and get our initial conditions from up here. Okay. All right, good. Awesome. Okay, good to go. Okay, so what do we have? So y0 equals 1. So when I substitute 0 in, I get c1 times cosine of 0 is 1. Sine of 0 is 0. And this will be 0. And that's equal to 1. And then the derivative equals, let's see, so substitute 0 into the first derivative. So we'll get minus 2c1 times 0 plus 2c2 times 1 plus 1/2 equals 2. So what do we get? So the first equation tells us that c1 is 1. And the second equation says 2c2 plus 1/2 equals 2. Divide everything by 2, I guess. And then subtract 1/4 from both sides. We get 3/4 on the right. And so therefore, what is our final solution? So y of x is equal to 1 times cosine 2x plus 3 over 4 sine 2x plus 1/2 x. That's it. There's our final solution. Great. Awesome. So there we saw the full process of how we go from an initial value problem, which is a differential equation like this one with initial conditions like this. And we got our general solution for this by first getting a general solution for this homogeneous equation, which is this one. And then we get our the form of our particular solution, which is right here. We substitute that in, we determine those coefficients, we get this as our particular solution, and then we put them together, we get our general solution for the differential equation. Then we use our initial conditions to determine these unknown C1 and C2 terms. We get them right here and here, and that's it. That is our answer right there. Happy. Great. So that is the full process. And it's all very straightforward. The thing that's probably the trickiest thing to worry about is this step here that we did, where you have to just make sure that these terms don't satisfy the homogeneous equation. And so you just keep multiplying by x until you get something that's different than what you have already, and that is not a solution of the homogeneous equation. But other than that, so it's sort of like the one thing you got to worry about, and it doesn't actually happen that often. So, okay, great. So I think that was it. Yeah. All right. So here we are. We're now doing one more method in this section. So there's another method for finding a particular solution to a differential equation that is more general than what we had before. So now we're looking at a differential equation where we may not have constant coefficients here, so they may be functions of x here. And we're also going to make, the most important thing is we're going to assume that this function here doesn't satisfy that initial restriction that we have with our other method. What is that other restriction that we had? Let me just zoom up here. Where is it? This restriction right here. So this one. So notice, in order to do this method of undetermined coefficients, we need our function to satisfy this. It has to be a sum of products of a polynomial, an exponential, and a cosine or a sine function. If this assumption is not satisfied, then we have to do this other method called variation of parameters. So let's go back down. Okay, so now we're going to look at this method of variation of parameters. And the idea is the following. So first of all, we need to suppose that we have a couple of linearly independent solutions of the homogeneous equation. So we may have to find that ourselves. Some of these questions in the book will just tell us what these functions are. So, but anyway, we need to assume that we are given a general solution of this homogeneous equation. Okay, so how do we find the particular solution? So this is a technique that always works to do this. It'll even work in that other situation that we were just looking at. What we do is, instead of looking, so we take this as the sort of the starting point, but we replace these constant terms, C1 and C2, we replace them with functions, U1 and U2, right? And so we're saying that this is our general solution of the homogeneous equation. Maybe if we replace those C1 and C2 with functions U1 and U2, functions of X, then maybe we can find a particular solution of this form that is a particular solution of the problem 3. And it turns out that this is always possible. This is always possible. And in fact, we're just going to do it for like a second order differential equation, but this actually generalizes quite nicely to higher order differential equations as well. So how do we do this? Let's see. So I'm going to go through the whole argument because we're going to end up with some formula for these U1 and U2 at the end, which are like, where did this come from? So we'd like to know where they come from. And so I'm gonna go through this this argument, and we'll see. And along the way, we'll learn some cool some other cool stuff that it would be useful. So let's see. Okay, so basically we want to take the derivative of this, the first derivative and the second derivative, and then we're going to substitute those into this equation here, and then we'll learn something from that. Okay, so let's start by taking the derivative of this. Maybe I'll just put like a bit of a divider here. So that's kind of like the setup. So now we'll move into the work part. So what do we need to do? So first of all, we'll take the derivative of this. So this requires a couple of product rules. So this is the derivative of this term. And then this here is the derivative of that term. So we're using product rule. Then we just reorganize this. We're going to take these two terms here, which involve derivatives of y1 and y2. So those terms go there. And then these terms involve derivatives of u1 and u2. So I'm going to put those there. Now, remember, in order to substitute this into the differential equation, we're going to need to take the derivative of this thing again, right? So now imagine we have like 4 things. We have to do 4 product rules, and we already talked about product rules. We don't like product rules. And we're going to get some like derivatives, second derivatives of u1 and u2, and that's no good. That's going to make our lives really bad. So we're going to make an assumption. It turns out this is always is the case, that this. So we're given some freedom. So we're going to use that freedom to say this thing, that's 0. So we're just going to make that 0. So turns out this works, and we'll see what we get. We'll see what we get. But that's one equation that we're going to have. So we're going to assume that this term here with these derivatives of u1 and u2, this term, 0. Okay, so that's great. So now we're just left with this. And now that's going to be much easier to take the second derivative of. Okay, so that's what we do. So we set this thing here. That is going to be 0. So that's what I wrote here right here. Okay, and let's give this a number. It's called 5. So this equation is 5. So that's one of our equations that we need. Now this thing is simplified. It's just this right there. Okay, so now take the derivative of that. And again, this is like a product rule. So this is the derivative of that. And then this here is the derivative of this. So you might want to check that I did everything okay. I think it's okay. And then we substitute. So here's our differential equation. So we're going to substitute this stuff here. We're going to put it right there. We're going to take this stuff. We're going to put this stuff right here. And we also had a formula for yp. So we'll put that there. What was that? This one right here. So we're going to take that and we're going to put that right there. Okay. and then we'll see what we get. And one thing that we're going to be using when we do this, this is going to be a mess, but one thing we'll use that will make our life a lot better is that these two functions, y1 and y2, they satisfy this homogeneous equation. So if we get something like this, like that, then that's equal 0. And if we get something like this, then that's also equal 0. So that'll also make things like it's going to be a mess, but a bunch of stuff is going to be equal 0. So it'll just disappear. Okay, so what do we get? So here it is. So y p double prime, substitute that expression in there. Y p prime right there. Y p right there. And that's it. So this whole thing right here, that's this. Now we need to reorganize this. Maybe I'll use my highlighter again to see what we're doing here. So it looks like we're collecting all of the U1 terms. So there's a U1 term. Where else is U1? Right there. And there's a U1 there. So we're collecting all that stuff together. And then we're also doing the same thing for U2. So there's U2 there, right there, right there. So let's just check. So what are the U1 terms? So we have Y1 double prime. We have a PXY1 right there. And we have a QXY1 right there. And then we do the same thing with U2. And we get very much the same thing. We get Y2 double prime, P of X times Y2 prime right there. And we get a Q of X times Y2 right there. And what are we left with? We're left with this stuff. So we're left with this term and this term. That goes right there. And now we can use our assumption that y1 and y2 are both solutions of the homogeneous equation, which means all of this stuff in parentheses, that's 0. All of this stuff in parentheses, that's also 0. So all of this stuff just goes away, just gone, completely gone. And we're just left with a much simpler equation like that. So once we get rid of all this stuff here, then we're left with this equation here, right there. So and that's equation number 6. So now we have these two equations. We have this equation 6 and we have this equation 5. They're both two very simple equations. They're equations that involve U1 prime and U2 prime. And there's another equation involving U1 prime, U2 prime. So we have two equations and two unknowns, and we can solve these equations. And the trick that we use to solve these equations is something called Kramer's rule. So Kramer's rule is a very useful technique for quickly solving 2x2 linear systems. So how does it work? So let's just go over Kramer's rule. You may have seen this before already, but imagine you have a 2x2 linear system. So two equations in two unknowns. So there's x1 and x2, and these are the coefficients of x1 and x2 in the two equations, and these are the two right-hand sides. So how do we solve this? Well, we actually have a formula for the value of x. So x1 is equal to the determinant of this. So it's actually, so first of all, we look at the determinant of this coefficient matrix here. So that's what goes down here. And then in the numerator of this, we also do a determinant, but we replace the first column, we replace that with the right-hand side, b1, b2. And that gives us x1. And we do the same thing for x2. Here's the determinant of that 2x2 matrix. And in the numerator, we do a determinant of the same matrix, except instead of this second column, we replace it with the right-hand side. And it just gives us like two very quick formula for the solution of this 2x2 linear system. And yeah, it's just very nice because taking determinants of 2x2 matrices, this is very easy. And notice that we're doing the same calculation here and here, so we just have to do that once. So we do one determinant there, and then we do another one here and another one here, and that's it. We've got our solution to the linear system. It's a really nice tool for quickly solving 2x2 linear systems. Okay, so that's what we're going to use for solving 5 and 6. So let's, right, I forgot I was going to do an example here. So here's an example. I think I grabbed this example from like a previous lecture where we needed to solve this linear system in two variables, C1 and C2. And so I think when we did it before, I think we like multiplied one equation by 3, and then we added them together, and then that gave us the value for C1, and then we substituted that in to the other equation, and we got C2. So there's like a lot of steps there. But with Kramer's rule, we can get the solution just like very easily. I find it's very nice to do this. So first of all, we grab the determinant of the coefficient matrix. So the coefficients here are 1, 1, and then 3, minus 3. So we do the determinant of that. And then in the numerator, we do the determinant of the same thing, but we replace this first column, we replace it with the right-hand side. So this top determinant is going to be minus 1 times minus 3, and then minus 1 times 15. So that gives us 3 minus 15, and the numerator in the bottom is 1 times minus 3 minus 1 times 3, so we get this. And then we just simplify. We get minus 12 over minus 6, and that's 2. So very quickly, we get the answer 2. And then we do the same thing, but now we replace the second column with the right-hand side, like that. So this bottom part, again, it's just minus 6. And the numerator is going to be, I guess I could just, like, let's just say this. We know it's minus 6. We know it's minus 6. So I'll just write that in. We already did that. So we don't need to do that calculation again, just to emphasize that. This numerator is 1 times 15 minus 1 times 3. So we get 15 minus minus 3, that's 18. 18 divided by minus 6 is minus 3. Boom, right there. So very nice, quick way to solve a 2x2 linear system. So now we'll do that for these two equations that we have. We have 5 and 6. So there's 5. You may recall, remember this formula 5, and here's the formula for 6. And we want to solve for u1 prime and u2 prime. So we just do this trick. We take the coefficient matrix here, y1, y2, y1 prime, y2 prime, and we take the determinant of that. You may recognize this as the Wronskian, and then of y1 and y2. And then in the numerator, we replace, we do a determinant, but we replace this first column with the right-hand side, 0 f of x. And then for u2 prime, we just do the same thing as that, except now we replace the second column with the right-hand side. Okay, what do we get when we evaluate all these derivatives? So as I mentioned, the denominator, that is the Wronskian. So I just write w of x there. The numerator is going to be 0 times y2 prime, which is 0, minus y2 times f of x. So we get minus y2 f of x. And then for u2 prime, we get y1 times f of x minus 0 times y2 prime. And so we end up getting y1 times f of x. And that is it right here. So this is what all the work that we're doing comes down to. Like, look at these formulas. Like, where did these come from? I mean, they're just crazy. But I think it's good to go through the details and see like where these crazy formulas come from. But these are the formulas, they work. And but remember, what we needed was not u1 prime and u2 prime, we needed u1 and u2. So the final step here is we need to integrate these two. So we end up integrating, so there's our formula, u1 and u2, right there. So I almost feel like we should celebrate this somehow. So let's draw some attention to this. Oops. All right, perfect. There it is. So there's our solution. Okay, so let's finally, we've got our formulas for u1 and u2. Let's apply these to this problem here. All right. So sorry about the long video. This is kind of a long section, so it's kind of a, yeah. Anyway, so it's a long section. I'm sorry for the long video. All right. So let's apply to this. Now, I guess we could have used our other technique that we learned at the beginning of this section, but let's use variation of parameters to do this. Okay, so let's see how it works. Maybe you'll like this one better, I don't know. So first of all, we need the general solution of the, I think my Apple Pen actually, my Apple Pencil actually died, which means I have to actually pause the recording and recharge my Apple Pencil. I'll be right back. Okay, I think it's charged up now. It's 10%, so it should be enough. It charges pretty quickly, actually. Okay, so where were we? Okay, so first of all, we need a general solution for this homogeneous equation. So let's write down the characteristic equation. See if we can solve it. Does this factor easily? I think so. 2, 1. So r is -2, -1. So our complementary solution is C1 e to the negative 2x plus C2 e to the negative x. All right, nice. Okay, so that gives us our y1 and y2. So maybe I'll make a note of that over here. So y1 is e to the negative 2x, and y2 is e to the negative x. Okay. So what's our formula? Oh, okay, first let's do the Wronskian. So the Wronskian, let's see. There's our Wronskian. Let's see. E to the negative 2x, e to the negative x, take the derivative. Okay, so this times this. I guess I'll write it out. And then I'll simplify. Minus that times that. Okay, so there we have it. So this times this minus this times that. Okay. Let's see, so we get negative e to the negative 2x. So we add exponents, right? So we get negative 3x, okay. And then plus 2 e to the, again, we add exponents, so we get negative 3x. Okay, so then Wx, the Wronskian is going to be e to the negative 3x. Okay, that's it. That's the Wronskian that we needed. And now we can figure out our other stuff. Let's see, add a page. Okay. So what were the formulas? So U1 was the integral. I think it was, see now I can't remember. I know it was minus, I was trying to think of the Wronskian, of the formula. Y2, yeah, Y2 f of x divided by the Wronskian. Okay. And then maybe I won't write down the U2 one yet. Let's just do this one first. So let me write it out. So Y2, what was Y2? Y2 was e to the negative x. And then f of x, 4 e to the x. Okay, 4 e to the x times 4 divided by the Wronskian dx. Okay, so some of this stuff is canceling. That stuff cancels, so that's nice. So we're going to get negative 4 e to the 3x. Okay. Negative 4 e to the 3x. So I just brought this up here and changed the sign of the exponent. Okay. And let's see. I think this is easy to integrate. So it's going to be like e to the 3x. When I take the derivative, I multiply by 3. So it's going to be like this. Yeah, that should do it. And I don't need the constant. I'm not going to write the plus c, right? See, I'm not going to write that. We don't need it here. We just need this this antiderivative here. So that will do it. So there's our u1. Okay, let's do u2. u2 is the integral of y1 f of x divided by the Wronskian. y1 e to the negative 2x. Times f of x, 4 e to the x, divided by e to the negative 3x dx. Okay, so u2 is, in this case they don't cancel, right? So we're going to be left with e to the negative x up here, and then we're going to add 3x to it. So that'll be e to the 2x, 4e to the 2x. Yeah, that's it. That looks okay. Okay. Take the integral. I think it's that. Looks good. So there's our two functions. And so therefore, the particular solution is u1, y1 plus u2, y2. Maybe not therefore. Then implies what? What do we get? Let's see. So u1, maybe I'll highlight this because this is kind of the important thing. So there's u1. u1 is that, u2 that, negative 4, 3, e to the 3x times y1, e to, what was that, e to the negative x? Yeah, e to the negative x, and then plus u2, e to the 2e to the 2x, and then times e to the negative 2x, and then we simplify. Negative 4/3 e to the 2x plus 2. Wow, nice. There it is. Great. So I'm not actually sure if you did the other technique on this problem, if you would get exactly the same particular solution or if you get a different one. Yeah, I don't know. It'd be interesting. I'm almost interested to try, but I'm getting a little bit tired. This is a long video. But it looks like we did what they asked us to do. We found YP, so we're done. So let's stop there. Let's stop there. It's good to be curious, but you know, yeah, let's stop there. Let's stop there. Okay, so one more of these questions. Now, this one we are given the complementary solution. So there it is. And I think we need to put this differential equation into the required form. So we need to make this initial term here, we need to make that 1. So we're going to divide both sides of this by x squared. So let's see, y double prime plus 1 over x, y prime minus 1 over x squared, y is equal to 72 x cubed. So that is our f of x. So that's why we need to do that, is because we need the proper formula for f of x. So therefore, f of x is equal to 72 x cubed, right? Not x to the 5th, right? So we had to do that. We had to do that step. So let's remember that. Now we have y1 and y2 are given to us. So y1 is equal to x, y2 is x inverse. So that's y1 right there and y2. So that's where I got those from. Okay, so there we go. And let's see. Let's see. So what do we do now? I guess we compute the Wronskian, right? We compute the Wronskian, and then we figure out what U1 and U2 are. So this method is actually not that complicated. So let's compute the Wronskian. So the Wronskian is y1, y2, y1 prime, y2 prime. Wronskian, x inverse, derivative. Let me just save some time here. So x times negative, so this times this, that is negative x inverse, minus this times this, x inverse. So we get negative 2 x inverse. Okay, so there's our Wronskian. So Wronskian equals negative 2 x to the negative 1. And now we compute u1 and u2. u1 is the integral negative u2. Let me just think, I always forget. Negative, yeah, negative U2, yeah, negative U2. I'm thinking of Kramer's rule. That's what I'm thinking of when I'm doing this. So Kramer's rule, thinking of Kramer's rule. Integral of, let's see, y2, I have it right here, x inverse. Oh, negative y2. F of x was 72x cubed, if I recall, and then divide that by negative 2x to the negative 1 dx. Okay, so therefore u1 is equal to the integral of, so we simplify a bunch of stuff, so negatives go away. 72 divided by 2 is 36. And then this x inverse cancels that one. So we're left with actually a very simple integral. That will be x to the 4th, 9, I think. I think that's right. Okay, not bad. So there's u1. There's u1. Okay, great. And then u2, integral of, now it's y1 times f of x. Yeah, divided by the Wronskian. What is y1? X. y1 is x. F of x is 72x cubed divided by the Wronskian, negative 2x to the negative 1, I believe. Yeah. So then u2 is, let's see. So in this case, we've got negative 36. We've got x to the 4th above and then divided by x inverse. So that's x to the 5th. So that's x to the 6th minus 6. Yeah. Great. So that's it. Perfect. Okay, so let's note that. So there's our U2. So we've got U1 and we've got U2. And now we just write down our particular form. YP is U1 Y1 plus U2 Y2. Okay. So YP is U1 9x to the 4. Y1 was x, I think. Y1 was x, yeah, okay. And then plus, actually not plus, minus. Okay. I hope I haven't made a mistake. So I've got x to the 5th minus 6, x to the 5th. So therefore, 3 x to the 5th. Man, that was a lot of work to get that. Okay. All right. So I think that's our particular solution. Of course, we could always check this. I'm going to check by looking at my notes. Is easy. Yeah, 3x to the 5th. Yeah. Got it. Was my other answer correct for 47? Oh man, I hope it was. What did I get on the other? Did I make a mistake? I might have made a mistake here. I don't know. I hope I didn't make a mistake. I got a different answer. There might have been a mistake in this one. Let me pause the video. I'm gonna check this because I might have made a mistake here. Let me just pause. Yeah, I did make a mistake. So the mistake I made was I've got these two things swapped around. So actually this was U1, or this was Y1 here, and this is Y2. So actually these two things should be swapped. So this one, put it over there, that goes there, and this one goes here. And then what do we get? E to the x, e to the x. So negative 4/3 e to the x plus 2 e to the x. So negative 4/3 plus 2. So this is negative 4/3 e to the x plus 2 e to the x. Six over 3 minus 4 over 3 is 2 over 3. Yeah, okay, that's now that's the answer I got. Well, I'm a little paranoid now. I did a lot of problems here. Hopefully, I didn't make any other mistakes like that. I'm glad I caught that before I posted this to YouTube. Let's see. So this question is, okay, that's the answer I got there. What about this one? That looks good. And this one. Yeah, that's good as well. Good. And this one. Okay. All right. Oh, was there another one that I did? I think that was it. Okay, so that's it. So there are the two methods that are covered in this section. They're kind of two very different methods for doing the same thing, but I think makes sense that we did them both in the same section. It does make it for a rather long section. So anyway, that's it. And I will thank you for watching as always. I hope you get a lot out of these videos and I hope they help. So thanks again. Bye for now.